Chemists, welcome to TP's Chemistry Cuts. In this video we introduce bond energies and then go on to use them to calculate enthalpies of reaction.
Bond energies are very straightforward. They're quoted numbers that tell you basically the amount of energy needed to break 1 mole of a bond, a given type of bond. And that would be in a molecule in the gaseous state. And we say the gaseous state because it means there's nothing else to interfere with the process of breaking the bond, no other forces involved, and so these things are limited. They're limited for two reasons. Everything involves the gaseous state, and so most reactions we do don't involve the gaseous state. A lot of things in industry do, but the things we carry out don't involve the gaseous state, and so this is approximate in that reason, for that particular reason. But also, if you actually look at what it means, what we're doing is we're taking 1 mole of a given type of bond, and I'll give you an example here. Hydrogen bond, that's nice and straightforward. There is only one molecule that has a HH bond in it, and that's H2 itself. And if you take a mole of hydrogen molecules, you'll find it takes exactly that amount of energy, 436 kilojoules of energy, to break every single one of those bonds. So the first thing to say is that you're involving bond breaking in this process, so all bond energies are positive in value because it's an endothermic process. So they'll always be positive. Okay? And in this particular instance, it's pretty straightforward. Hydrogen's a gas, so you can work this value out experimentally quite accurately. But let's have a look at something like CH. Okay? If you look at a CH, don't need to write any of this down. This is just so you get things into perspective. If you look at these three molecules, okay, they've all got CH bonds in them. Okay? And you think, well, we can work out a CH bond enthalpy, can't we? And you say no, because the amount of energy needed to require, the strength of a bond relates to the amount of energy needed to break it. Okay, the bond energy. And what you'll find is if you change what attaches to the C of what CH is forming, it actually changes the strength of these bonds. And it makes a lot of sense. If we look at this one, we know that fluorine is one of the most is the most electronegative element in the periodic table. It's sucking electrons towards it, so it's going to suck them out of these bonds. So it's going to weaken them. Methyl, and we don't cover this at school, but methyl does the opposite. It pushes electrons. It doesn't want any more electrons, it pushes them back. And so these bonds tend to be a bit stronger. And this one is somewhere in between. So what you're finding is that the strength of a given type of bond depends upon the environment around each of the atoms that form that bond. And it varies from molecule to molecule. And for things like organic chemistry, where there are millions of molecules, particularly millions of molecules that involve things like CH and CC, then you have a problem. And so what we do is we quote sort of an average value from the multiple of data, experimental data that's been collated over years. And that means not only are these fairly approximate, so these values are not going to be spot on, but also it depends where you look as to what values you get. So some places you'll look up the values, and if you're doing a problem online, you find some problems and you'll see a set of bond enthalpies quoted. They may be different to the ones that we quote, only very slightly, but still different. So take it in mind, and that's why I said take it into context. These things are very variable, and the idea about using bond energies in calculations is to give you sort of ballpark figures, give you an idea of whether something is an exothermic or endothermic reaction, whether it's massively endothermic or massively exothermic, and so on. So it's a very quick way of being able to judge that. Okay? So what we will do is we will look at, I've given you a sheet, okay, with some problems on it. And at the top of that sheet, can I ask you to stick that in your book underneath what I've written there? Because this is all you need to know about bond energies. We're going to look at how we use them to calculate the enthalpy of reaction. And I've quoted a whole series of common bond energies there. Okay? And you'll see, as I've said, they're all positive. Now, another thing that you need to note, if you look at something like a C double bond C, that is not equal to 2 times a single bond. It's not the way it works. So when we come to look at how we use these things, if you can't see this immediately, don't just think, oh, I'll take 2 times C single bond C, because you'll get it wrong. Okay, you must use the correct values. Okay. So how do we use this? Well, we can use it to calculate an approximate heat or enthalpy of reaction. And we use a very simple equation, which you're just going to have to memorize. There is an easy way. Okay? We have these acronyms. We always use acronyms to remind ourselves, well, this one's a nice, neat one, because it's BURN. And I think you can all remember that one. Okay? And that means bond energies use reactants minus products. Okay? Now you'll find when you come to do a bit more thermochemistry that sometimes you take values from the products and you subtract away the reactant values, and then other times you use the reactants and subtract away the product ones. This is that latter one. Okay? So this will make sense in a minute. So I'm going to write out the equation and then explain it. If we take a simple reaction, I'm trying to think of one that, okay, this one here. What you're going to need to do is to draw them all out as structural diagrams without the Lewis diagrams, without the non-bonded pairs. We call them structural diagrams. So if we draw these out, what we've got is H, Cl, Cl, and then we get 2 HCls. Yeah? And what we're going to do is we're going to break these, okay, and then we're going to make those. Could somebody look up the value of this? 436. Sorry? 436. Okay, what about this? 242. So, if I add those two together, okay, then that is 678 kilojoules. Yeah? And I'm needing that to be put in because I'm going to break those bonds, aren't I? So do I put positive values or negative values? Positive values, because you're breaking bonds, okay? So this is the reactants. This is the products. Now, I'm forming 2 HCl bonds. What's the amount of energy needed to break those bonds? Look it up. 4, 3, 1. But there's 2 of them. Yeah? Now, I'm forming them. What do I need to put here? It's got to be negative, because energy is given out, because I'm forming bonds. Just to clear it up, just to remind you, bonds break on this side when they react. Here, bonds form. Okay? So to break the existing bonds, I need to put in that amount of energy, and to form them, I need to put in that amount of energy. So all I need to do now is take that number and add it to that number, and that gives you the overall effect. So the delta RH is equal to that, plus 678, okay, which is what I needed to put in to break some bonds, and minus 862, which comes out when you form the new bonds. And this is all done in terms of moles, so it's a delta RH, because I've done the moles for the equation. Yeah? So can somebody...
So just go back. So you don't subtract the negative?
No, you don't subtract the negative.
Okay.
But you will subtract the negative, because I've made it into negative, because it's going to... I'm trying to explain it in terms of energy in and energy out. So it's as simple as that. Can somebody work that out? Minus 184 kilojoules per mole. Now what I've actually done here is, if you want to get this as a mathematical equation, is I've actually did a bit of a fix here in that I said, oh, energy is given out, so I changed the sign. Remember, they're always positive. So that's why we say reactants minus products, because you're going to change the sign for all the products because energy is being given out, so you need it to be negative rather than positive. Okay? So, if you see this, you may well be given this one. It's written in a freaky looking way. Actually, it's okay. So yes, this is a Greek sigma, capital Greek sigma, and it's used in maths a lot, in physics and in chemistry. It's a standard symbol, which means you're summing up things, so you're adding them up. So what this is telling you is, if you want to work out a delta RH for a reaction, an enthalpy of reaction, look at the bond energies for all the bond energies for the reacting particles, sum them all up, and then take the bond energies for the product particles, all of them, every bond angle in every single one, allowing for these numbers as well, for it's a balanced equation, and sum them up, and then take these values and subtract them from there. What I've tried to do is to show you in a very simple reaction why we're subtracting them. And then what I would say is this takes a little bit of a while, but if you get a reaction where you've got to work out delta RH from bond energies, do this. Write out your equation, write out fully, it won't be a simple equation like this, all the bonds for all the molecules, count up each type and work out the sum. And we'll do one that's a little bit more complicated in a minute. Okay? You can work it through. So then you can take the reactants and subtract away the products. Should we try one that's a bit more complicated? Has anybody lost this? Hopefully. What we've got is CH4, which looks like that. And then we've got two oxygen molecules, which is O double bond O. Okay? We're going to form a carbon dioxide molecule, and then two water molecules. Okay? Now you can see why it's a really good idea to write everything out. Do not try to do this in your head from the equation, because you will miss things. So the first thing is, I've got 4 times CH, which is 4 times how much?
430.
430.
13.
413. Okay. I've got 2 times O double bond O, which is 2 times how much?
494.
494. Okay. Now, 2 times C double bond O, because each molecule of carbon dioxide's got 2 of them, not 1. And that's where people often make a mistake, particularly with water, which is 2 times whatever that is.
745.
Okay, and here we've got 4 times OH, which is 4 times 463. So, some people need to work out this sum. So, 4 times 413 plus 2 times 494. And then we've got 2 times 745 plus 4 times 463. So this is reactants, this is products. 2640. And what about this one?
3,342.
3342. So I take that minus that, because it's, so reactants minus products equals 2640 minus 3342, which is equal to
-702.
minus 702, and this one is in kilojoules per mole, because you're doing it for the thermochemical equation here. So delta RH for this equals minus 702 kilojoules per mole. And if you look it up, that won't be the correct value, but it'll be quite close to it, because the correct value will have been worked out from experimentation. We're using approximate bond energies. It's a different type of calculation, where you're given delta RH, and you've got to work out one of the bond energies. Now, this is a slightly different problem, in that I'll make it a simple reaction. You've been given some of the bond energies and the delta RH, but there's one missing. You've got to work out the bond energy for N triple bond N. So if we write the whole thing out, do the same process, okay? We've got N triple bond N, and then you've got 3 of these. Again, I've kept it simple. Don't expect yours to be simple. And then you've got N so you've got 1 times N triple bond N. So we'll just say X for that, because we don't know what that is. Then you've got 3 times HH, which is 3 times 436. Okay. And then you've got 6 times NH. Okay. Which is 6 times plus 391. So, what's this equal to?
1,308.
Okay. So if we're using delta, this is the reactants, this is the products. The reactants is X plus 1308 minus 2346. And that's equal to 92. Minus 92.4. Get your signs right. Okay? So you notice I've put this as plus now, because everything's plus. and then I'm putting a minus sign because it's energy given out. Yeah, that's why it's the minus. So if I now rearrange this, x is equal to minus 92.4 minus 1308 plus 2346. Somebody tell me that? 947.6 kilojoules per mole.
45,
Sorry?
45. 945.6.
Okay. And it must be positive because it's a bond energy. So if you get a negative number, you've done something wrong somewhere. But can you see what I've done there? Very simple. Okay. So you calculate the two positive values, make this one negative, and that's equal to the delta RH. Where did I get the? They're up here. Quoted them. You will be given these, and you've got to work this one out. Try that one. What's C single bond C? It's not on that list, is it?
Double bond.
No, that's double bond. So if you want to write onto that list, in fact, why don't we do, is there a C double bond?
Yeah.
So why don't you work out the C single bond? Off you go. So you've got 3 times CH. We've got 1, 2, 3, 4, 5, 6 times CH. 1, 2, 3, 4, 5, 6, 7.
Wait, is that the reaction?
Yeah. That's the actual reaction.
That one there?
Yeah.
HCCC.
This is going to be quite harsh.
You know, like how this is one bond.
Now, what you're saying is you are going to work out this. 6 times CH. 6 3s are 18, 6 1s are 6, 7, 6 4s are 4. 1 times CC is, how much is CC?
619.
You've got X plus
So what about the HCl? Where's CC? Yeah, that's right. How's there, where's the CCl though? CCl bond.
Is this yours?
Oh, the top.
So what we've got is that bit there minus that bit there equals minus 1, 1, 2. So, burp, remember to burp. Okay. Delta RH is equal to the sum of all of these minus the sum of all of these.
So you need the minus 6?
Yes. So it's a minus because we're swapping it from being positive to negative because this is giving energy out.
But you've forgotten your minus 6.
Minus 2x.
Yeah,
This is
x
2.
minus 2x is minus x.
No, x minus 2x is minus x. Yeah, that's fine. And we're going to work out what x is. Okay? So, if we've now got what we've got, x minus 2x is minus x, then we've got 3258, and you're subtracting 3230. 3258, and you're subtracting 3250 from it, yeah? 30. 3528. I'll get there in the end. Okay? So you've got 3528 and you're subtracting 3230 away from it. Yeah? So let's do that, shall we? 2, that goes down to 1. 3 from 11 is 8. That goes down to 4. 2. Yeah? And that's equal to minus 1, 1, 2. So if I rearrange that, and this is where all the maths people start to go blob, I can't do maths, I can add that to this side, because I need to be positive. I can't have a negative number, can I now?
It's 298.
Yeah, 298, so.
So I did do it by hand. Okay, 298. So, if I bring this to this side and that to that side, I get x is equal to 298 plus 112, which is 410 kilojoules per mole. Easy!